think when I say lasers in space?
Lightsabers.
What do you think about when I say space and airborne laser platforms?
Death Star? What else?
What do you think about when I say laser-based propulsion for space travel?
Ooh, freaking complicated navigation math with way too many variables.
Okay, no, seriously. In the next talks, we will learn what's really behind these terms. Peter Buschkamp will teach us not only basic physics, but he will also teach us about the boundaries of lasers in space.
And we will learn about space travel with lasers, which absolutely sounds like science fiction, but apparently is already a reality.
Peter Buschkamp works for the infrared group of the Max Planck Institute for Extraterrestrial Physics, where he's building the world's most sensitive instruments for space observation.
He's also active in the Munich Freifunk community, where he's building backbones. And he was the head of the Public Astronomical Observatory in Bielefeld.
Are you sure about the Bielefeld part?
Yeah. Please give a warm hand for applause for Peter Buschkamp.
All right. Yeah, this is essentially a follow-up talk from last year. I don't know who was there last year. I talked about how to shoot lasers into the sky and use them for astronomical purposes, essentially to correct the atmosphere above us to get clean and undisturbed images here on the ground and not just from space telescopes on satellite platforms. So this year it's lasers in the sky. It's only 30 minutes, sorry. I will give a brief overview of some topics, what is actually now already flying above our heads, what some people think should be flying soon above our heads, and some others are pure speculation. So first we'll talk about laser propulsion. Actually, this is the second reason how this talk came to be, because I was talking to Liz and she wanted to do something about interstellar and interplanetary colonization, and I said, okay, cool, maybe we can combine it and then talk about also about photonic propulsion and so on, and then we just skipped it into the next talk to have more time for other stuff in the other talk. After that, we're talking about laser brooms, how to clear up the skies above us with lasers. It's going to be about laser sensing, which is routinely employed every day. If you look up the weather on your smartphones, there's a fair chance that you will be looking at some refined laser data that has been taken either from ground into space or from space to ground. And to finish, we'll talk a bit about laser communication. Of course, this is something a lot of people here in the audience are also interested in. It's the Chaos Communication Congress, after all. And this is something that takes place above our heads, is being built right now, and is actually pretty exciting. So first, let's talk about laser propulsion. Laser propulsion is a method of pushing something forward with just light. How does this work? Well, I mean, photons are not just there to illuminate things, which they do a pretty great job in. They also, of course, carry momentum. It's just a tiny bit. It's their energy divided by the speed of light. But still, there is a bit of momentum being transferred from a photon when it hits some surface. To get a rough idea how much this is, if you are in Earth orbit, you get the amount of photons from the sun, which is equivalent to the so-called solar constant, which is 1,361, I guess, if I remember correctly, watts per square meter. This translates then if you have a solar sail, which you put into Earth orbit, and just let the photons from the sun push it forward, which is equivalent to, well, it depends a bit on your orientation of the sail, and if it's a black sail, photons get absorbed, or they get ideally reflected. If you have that means if you have an inelastic collision or an elastic collision for the physicists here in the room. But roughly you get around 7 micronewton. That's not much. Of course, this is not much. Well, you can scale up your sail. It's not just 1 square meter, maybe it's 100 by 100 meters. The point is, it may be just a very tiny fraction from each photons, but there are a lot of photons, and this is for free. So if you maybe have a mission which you just want to push far away and you have time on your hands, maybe this is something you want to do, because this is constant. It's not like a chemical rocket which burns off after some time. You don't have to bring huge amounts of propellant into space for that. This could maybe an option. Is this pure science fiction right now? No, actually not. This is a representation of a test solar sail satellite from the Japanese space agency, which has been launched in 2010. It's called Icaros. And there you get a rough idea what this actually looks like, because if you this is just a sail with something in the middle. But yeah, this is actually flying right now. They hope to, they last communicated with it in 2014. They hope to communicate in the next year with it again. And what you see here is in the middle, for example, there is the little payload. So some experiments, a little transmitter to communicate back to Earth, and these blue stripes you see around the middle, these are actually solar cells which then produce the electricity for the experiments on board. How big is this thing? It's 14 meters by 14 meters, so this is not much, but it's a nice technical demonstration platform. Of course, if you want to go really into serious propulsion with that, you rather look maybe at sails which are 100 meters by 100 meters or even a kilometer. We don't have a real clue yet how to make them, how to bring them into space, what to use actually as the sailing material, how to unfold it properly, but we'll eventually get there. Another thing you could be thinking of is, of course, not the sun, but, of course, to shine a big laser on this, maybe a ground-based laser, maybe a space-based laser. There is, of course, Project Starshot. It's going through the media all over the place right now. This is a very interesting concept which uses a ground-based or maybe a space-based laser. And of course, there you have targeted and directed laser light, so you don't have the 1/r² problem when you get far away from the sun. This is an option. Another option using lasers in a similar manner is not to just push the sail forward with your laser, but to use the laser actually to transfer energy to your spacecraft. And this is a so-called laser-energized, laser-based propulsion. This is nothing like a sail, although this might look like it. I like these 60s and 70s space art. So on the very left, you see a laser array here in some orbit around one of the moons of Jupiter. I think it should be Io because of the geyser there. Anyway, so this is sending out a powerful laser beam to one of these reflectors on the spacecraft itself. In the front, again, there's the payload. At the very rear, again, there's the engine. In the middle, there's everything else. And so what we do here is we do have propellant on board. But unlike in a chemical rocket, where we use the propellant for the energy and also the debris from the propellant, the dust and what comes out after the reaction for the thrust, here we use some external means of energy transfer on a propellant, which gets then pushed out of the nozzle of our propulsion system and then pushes the whole thing forward. If you think of a normal jet engine, it's the same. You use air as the medium and you use kerosene as the energy to actually drive the engine. Another very interesting thing which is being discussed in the scientific literature right now is the so-called photonic laser thruster. And for some applications, also in military application, there is the great wish for having formation flying satellites, which also maybe are flying together like this, and then they expand into a nice formation and have a nice long baseline between them, and they should get together again. For some radar, for some interferometry of radar on the ground to see where you know, yeah, all this kind of stuff. This can be done with tethers, to just have a rope between those. But if you have small satellites, you maybe want to think about something else, and this is then what you do. So you have a laser between those two vehicles, the mission vehicle and the resource vehicle. Can also be of comparable size, doesn't matter. The interesting thing is here, you do reuse the photons. It's not just that you shine them on a reflecting surface, like on a sail, or as we've seen in the other case, but you have them actually enter like a laser cavity. There are mirrors to each side of this, and so you reuse the photons, and this is very efficient in pushing two small masses out of each other, and then if you just switch it off, they will self-gravitate together again. This is a very nice thing to have formation flights. At least it's proposed. It's not yet demonstrated in space, but we'll soon see this. Laser brooms. If you look at the Earth from far away, or maybe not even so far away, within the orbit of our moon around Earth, and if you exaggerate a bit, this is how it looks like. Earth is enshrouded by junk right now. This junk has been put there by us. We have 50 years of space exploration, upper stages of rockets having collided, tanks being ripped off, satellites who have collided, and this makes up a huge amount of space debris, as it is called. There are around 30,000 objects of the size of 10 centimeters in space around Earth, about 700,000 of the size of 1 centimeter, so some thumb size, and over almost 200 million of them smaller than 1 millimeter. So the ring you see here is, of course, the geosynchronous orbit, and in low Earth orbit you also see this. Is this a problem? Yes, this is a problem. Here you see a nice image from ESA at the, I think it was in this September 2016. Sentinel-1A is one of the new class Earth observation satellites from ESA. And actually on the left, you see how one of the solar panels looked like before the impact. And then on the right, you see, yeah, there was some space debris hitting the satellite. And there's about 40 centimeters in diameter damage on one of the solar panels. And this roughly corresponds to some space debris junk piece of around 5 millimeters or even less. So we have to think about if now space traffic is increasing and how to get rid of this. One concept is to actually shoot at this from the ground. Of course, not in a matter that you now destroy these pieces and just split them up in even smaller pieces. This is not what we want to do. Of course not, because we want to reduce the size. How do we reduce the size of these things? Well, if we get them into an orbit that they will just gradually go down in Earth atmosphere and just burn up in the Earth atmosphere, problem solved. And this is actually what is being proposed right now. And if you take a commercial high power laser around 5 to 10 kilowatt, which you can buy, and put it on a decent telescope, you could move the orbits or the orbital velocity of space debris of around 1 to 10 centimeters by 1 millimeter per second in only shining your laser at it. Again, it's like a solar sail. It's just pushing the stuff with photons. So it will have a slightly different orbit. It will then go into Earth atmosphere and then just burn up. Of course, this has also been proposed from space. Actually, this is the same guy who is now in this Project Starshot project. Lubin et al. And Cosmo et al. 2015. If you want to look up those papers, they're quite interesting reads. And for example, this is a proposed satellite that flies now in deeper space. They did not just think about deflecting space debris, but also here targeting asteroids. So this is a platform which has big arrays of solar cells to power the onboard lasers. And then we just shine this laser at the asteroid for quite some time. So it could be a year, it could be maybe 10 years. If we identify the threat to Earth early enough, this is easy. Also, by the way, if you're interested in this stuff, there is a conference about planetary defense conference. Just look it up, so you can take part. People are discussing seriously about this. What you do then is not to just push the asteroid with your photons, but here asteroids very often contain frozen material, frozen gases. So you sublimate those gases, and actually, while the gas sublimates from the asteroid itself, it creates a bit of thrust, of course. It's just like a little chemical rocket thruster, and that gradually pushes things out of the way. This is the so-called D-Starlight mission, as it's called. There's also a D-Star, which then proposes to have a dedicated, shown on the left, laser platform with even more powerful lasers, and then have an array of mirrors somewhere in space to direct this, for example, to an asteroid. Maybe this just needs half a day each day for 5 years to be deflected, so it will not hit us in 30 years from now, and then we turn this mirror in another direction and just to push a bit our spacecraft, our solar sail spacecraft, like the Project Starshot thingy, which we want to push through space. This could be done. It's shown here in detail how you would do this with an asteroid. As said, you just sublimate the gases there and use them as thrusters. This is, of course, not what we do have in space right now. It's being proposed. What we do have in space right now is laser sensing. Laser sensing is so-called LiDAR. It's light detection and ranging, like radar. And what we do is we do have a transmitter on a spacecraft. It shines down into the atmosphere. It's a pulsed laser, just like the laser in last year's talk, which we shoot upwards. So we know exactly when we started the pulse and where it is after a given time. So if the pulse travels down into the atmosphere, it will, of course, traverse different parts of the atmosphere. And thereby probe different layers, maybe high clouds, high winds, more lower winds, or something like that, and it will backscatter. And we, of course, know the time the light travels downward and upward. And so if we make a graph of the signal intensity versus time, we can learn about the different heights in the atmosphere. We cannot just do this with one laser. We can maybe do it with 2 lasers, and therefore use different wavelength. That means looking at how the one wavelength is absorbed by the atmosphere, and then looking at how the other wavelength is absorbed by the atmosphere, and then correlate this, and then maybe even learn something about the chemical composition of the Earth in our line of sight. Or we do something like Doppler shift measurements, and there we can learn about, for example, how wind is blowing in the atmosphere. So our timeline is essentially, as said, the distance from our spacecraft, which then translates to altitude. So a short just means it's near to me, it's the high atmosphere, and the far away time signal is, of course, then the ground layer maybe. This is hopefully being launched next year. This mission has been on the menu a bit longer. It was a bit delayed. This is ESA's new satellite for just profiling the wind, and you see here an artist's description on the right. The only actual instrument on the satellite will be this wind LiDAR, and it will probe down into the atmosphere and give you exact measurements how the wind is blowing. So this will then use this Doppler method where you send out a signal and just measure the shift in frequency from the return signal, which is then influenced by if you have maybe hit something that is receding from you or coming towards you. Of course, you have to calculate out the satellite motions itself and Earth motion and blah, blah, blah and whatnot. So this is hugely complicated. And if you want to have a look at the instrument, it's looking like this. And this is another lesson. We had this in the talk before. Space technology is really, really hard. I'm not saying it's not possible. It is possible. It is being built, but it's not just you don't just fumble something together. And who has ever we have heard by in Andre's talk about the microscopes and how to build your own microscopes for maybe doing laser microscopes to enhance the resolution and how to build them on a typical optical lab bench. Here you do essentially the same, but also you have to launch this thing. And actually, this is the most critical part because this will be shaken like hell. And whoever has adjusted a laser resonator alone mostly is not a fan of, just come into my lab and kick my table a couple of times and let's see if it's still working. This will be happening during launch. And so you have to really make it perfect and test it 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 again. And when you think you have done enough testing, you test some more. Another thing, of course, you can make distance measurements. This is used on the European autonomous transfer vehicle, the ATV that docked to the International Space Station. This is how it looks like, and there's a little LiDAR interface on the side, and it sees the International Space Station then in false colors, which mean this green stuff is very near to me. There's it's the flange where I have to dock. The red part is then at the very back. This is the truss structure of the International Space Station, and the whitish thing in the middle is one of the Soyuz capsules that is right now docking on the International Space Station. So this is being used routinely now in space, and as said, you can maybe see it in your weather app on your smartphone every day. I'm not talking about this one. This will be in the later, actually maybe in the next talk. You can also do gravitational waves, and there you have to communicate between different satellites, not in terms of just exchanging data, but you're actually flying a Michelson interferometer in space and measure the relative distances between three satellites separated by thousands of kilometers in space to detect gravitational waves. We'll learn about this in the next talk. So in the remaining time, let me briefly give you an overview of how our communication is actually affected by lasers in sky. This is mostly developing right now. So the first satellites who employ this on commercial platforms are already in space. The next will be launched next year and the years after that. Why do we want to do this? Laser communication. I mean, can't we just do the normal Ka or Q-band radio frequencies, which we are using? I mean, satellite TV, it's working fine. The thing is, of course, with laser communications, you do have a much higher bandwidth. And that means you have several tens of gigabits per second per channel. It's very, very efficient. And this is actually interesting for space then again, because you have learned in the previous talks that each kilogram you want to put into space costs you a lot of euros. And so if you look at radio frequency, you get about 0.5 megabits per second per watt. So electrical consumption and kilogram. If you're using if you're looking at a laser communication system, it's more in the range of 5 megabits per watt and kilogram. The communication terminals are smaller, and they are. And if you, for example, have a satellite pointing just down on Earth with its radio footprint, the radio footprint is really, really large. If you do laser communications, you can get down your, even with a small telescope of about 20 centimeter size in diameter on your spacecraft, you can get down your footprint on the Earth to about 6 kilometers. So this is a very, very tiny spot. So if you're the only one who sits in the middle of the desert observing the signal, so nobody is going to be eavesdropping on you. Also, there are some ideas how to do this interferometrically, and then if you actually were to intercept the signal, you would destroy the interference pattern, and this is not going to work out. This is how it roughly looks like, what we want to do. So this is what we have right now. It's the radio link between a ground station, also called ground segment in space lingo. And this is the satellite bus up there. Yeah, it's called satellite bus. Don't be, it's just called like that. And it has the payload then on top. So if you ever read payload and satellite bus is the satellite, and payload is the stuff you put on there to do the actual thing you want to do. This is, for example, in geostationary orbit for satellite TV. But there are other things also flying around in geostationary orbit or in low Earth orbit. And in low Earth orbit, you see that the orbit just vanishes behind the horizon there. So if you have maybe a satellite that looks at Earth, like probing the wind, like we've seen before, it is only visible from your ground segment, from your ground station, for a brief period of time. Who has done SDR radio on the NOAA satellites? Anyone? Oh yeah, okay. So those people do know what I'm talking about. So you have about 10, 20 minutes. If you have a real nice position where you can see the satellite, where you can record the weather image that gets transmitted from but after then, nothing. So it would be nice, for example, to have an optical link, high data rates, as said, to one of the geostationary satellites, and then have them maybe over a hub, then talk to your low Earth orbit, maybe then over other hubs when it gets out of the reach of the one geostationary satellite, and so on. So this could be really interesting. Again, yes, maybe radio also, but as said, high data rates and all the pluses that come with the lasers. So for the technically inclined in this audience, it's how do we communicate? We have 3 different types of modulation. This is the on-off keying, the OOK. That just means you switch your laser on and off, Morsing. It's what you have in your fiber line card maybe at home. It's what you do from ground to space. You have pulse position modulation. This is what you have in your TV remote. And actually, jump, 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 jump. Perfect. So this is what you do from. All right. This is what you do from ground to space, because this is very immune to disturbances by the atmosphere. You still have to look through the atmosphere. If you have nothing in your line of sight, you can of course go to nicer modulation principles like binary phase shift keying or higher modulation schemes. But this means then if you modulate the phase, that you do not want to have a medium in between which is disturbing your phase, and this is the atmosphere. So this is only used for space-to-space links. This is how a laser communications terminal looks like. You have the laser and everything down there somewhere at the bottom. You have 2 mirrors reflecting it then out of the central aperture at the very front. It's about 13 centimeters usually. And this is how it looks inside. So the laser is at the very bottom there. And then you have diverse mirrors in there to get actually the laser out. As said, different modulation schemes are being used, different frequencies are being used. Typically, if you want to reuse telecommunication equipment off the shelf, you use 1550 nanometers. You get this in the normal telecommunications industry. If you want to, for example, apply a neodymium laser, the infrared part, you go for the 1064 nanometer. And people are working together in space. So, for example, here it's the Lunar Laser Communication Demonstrator from NASA talking to ESA's ground station in Tenerife. And this is how it then looks like from space. Actually, there's no video online, but yeah. If you look at the communications unit, there is the optical module. This is just the laser, but of course, internally you need controller electronics, you need a modem. But the nice thing, as said, is if you do this standardized, you don't have this complicated setup you have, for example, seen in the experiment for the wind measurements with the LiDAR looking down. Here you just take commercial off-the-shelf units from telecommunication industry, slap it together, and you're good to go. You can also do this for deep space communication. This was a mission proposed by NASA. Sadly, it was cancelled to do this up to Mars. You can do this from satellite to satellite. This has been done with the TerraSAR satellite from ESA and the NASA EnFire satellite. And right now, the Europeans building a data relay system around Earth. It's called the EDRS, the European Data Relay System. It's hosted on a commercial satellite from Eutelsat and a dedicated satellite that will be launched later. And you see here the laser links, for example, in red between the satellites, or in green to the International Space Station. And then they have also radio frequency links down. The next step is already in the works. It will be the so-called GlobeNet. So position various satellites on a geostationary orbit around Earth, having intercommunication from satellite to satellite on laser-based. And of course, the next step will be this one. And my personal interest would be then to have this one. Is there anything else? Yes, I know that in the abstract I did mention weird stuff. Communication, laser-based, from submerged submarines to satellites in space. Yes, this is being done. Downside is you will not find any open access publications which you can show, which can be streamed into the internet. Just Google for it. You will find really nice sets of information there. It is that for certain frequencies in the blue and in the green, actually the ocean is pretty transparent to these laser wavelengths. And so you don't need something floating on the surface of the ocean and then maybe have a fiber line down to your submarine and then, no. You just shine the laser at the ocean. And you do this the other way around too. Just look it up. It's pretty interesting. Some of the stuff has been declassified. Well, actually, this is the only source which I also have because I don't work in this kind of stuff. And if I did, I couldn't tell you. Yeah, so there's a lot of stuff going on in space above our heads right now and in the near future. Just watch out with your spaceship if you do the asteroids. We don't want to see that. Okay, next talk. Thank you.
Thank you very much for this amazing talk. We perhaps have time for one short question.
A really short question.
So there's somebody already on the microscope. He's waving. Do you get a short question, number 2?
Yeah.
Try.
Okay. It's just about how far the weather affects communication. We had a company that had 2 locations and tried to do laser communication, and it turned out fog is evil, snow is even more evil. So how is it from space to Earth?
Yeah, you do have these problems, of course, too. you do have, the only thing you can do is maybe use modulation which is more immune to it. Otherwise, if you have really dense fog, you're at some point just out. And therefore, the ground link segments are often still, as you've seen, for example, in the GlobeNet, in the European Data Relay System, the ground links are always at least backup with radio links.
So it's also getting a little too loud here to answer questions, really. So if you have any more questions, just come here to the front and ask Peter directly. And now we want to end with a last big round of applause to thank our speaker, Peter.